part 2 of your video on 5.6 related rates. This gives us yet another different type of situation. We have a police cruiser approaching a right-angled intersection from the north. It's chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, we want to know what is the speed of the car. So in this one, I'm actually going to draw my picture first so that I can get an appropriate variable to represent the speed of the car, but that is going to be a rate. So we have a police car approaching from the north. It's approaching a right-angled intersection, and then we have a car that's moving to the east. So the police cruiser is it's approaching from the north, so it's actually heading south, and then we have this speeding car that's moving to the east. We know that, let's call this y and this x. Those are going to be constantly changing values because the police car is moving closer to the intersection and the speeding car is moving farther away from the intersection. So we know that when y is equal to 0.6 and x is equal to 0.8, it says the distance between them and the car is increasing at 20 miles per hour. So we are considering the distance in between them. We know that dr dt is equal to 20 miles per hour. We know that the cruiser is moving at 60 miles per hour. So we know that dy dt is equal to 60 miles per hour, which means the speed of the car is going to be my dx dt. None of the quantities in this problem are fixed, so there's no numbers that I can plug in before I set up an equation and take a derivative. And I'm not talking about angles here. I know I do have a right angle, but I'm more concerned about the sides and how the sides of this triangle are measuring. So this is going to be a Pythagorean theorem type question. So we have r squared is equal to x squared plus y squared. Now, it does not tell me what the distance is between the two cars when the cruiser is 0.6 miles north and when the other car is 0.8 miles to the east. So I don't actually know the value for r. You could find it. I mean, you could plug in 0.6 and 0.8 0.8 for x and 0.6 for y, and you could go through and solve for r. But if you want to avoid doing that, before we take the derivative, we can actually solve for r by taking the square root of both sides, and we're going to get the square root of x squared plus y squared. Now, you do not have to worry about the plus or minus with this because I'm talking about a real world situation. So even though there's both a positive and negative answer that would work here, because you're talking about real quantities, we don't have to worry about the negative aspect. Now we can take the derivative. So dr dt is going to equal, this is 1/2 times x squared plus y squared to the negative 1/2 times the derivative of the inside, which is going to be 2x dx dt plus 2y dy dt. And remember, dx dt is what I'm actually looking for to solve. I'm going to scroll, give myself some more space to do some math here. I am going to go ahead and rewrite this before I solve, before I plug in anything. So dr dt is going to equal the x squared plus y squared to the negative 1/2 power. That's going to move to the bottom. And it'll be now to the positive 1/2 value. You have a 1/2, so 1/2. The 2 would normally go on the bottom, but I also have this 2x and 2y. So I can actually distribute that and get rid of those 2's. So I'm left with x dx dt plus y dy dt on top. Now I'm going to go and plug things in. I know dr dt is 20. I know x is 0.8. I don't know dx dt. I know y is 0.6. I know dy dt is 60. And then on the bottom, my x is 0.8. My y is 0.6. And then that's to the 1/2 power. So then I would go through and do the math to solve this. So this is 0.8 dx dt plus 0.6 times your 60 is going to be, I believe, let me see here, it's a little bit different than how I did this on my own. 36. Okay, that was what my initial instinct said. And then in the bottom of our fraction, 0.8 squared plus 0.6 squared is actually equal to 1. And so when you take the square root of 1, you're still just going to get 1. So we are going to have to, and actually I believe this, this 60 here is negative. Let's see here. And the reason that's negative, because you do have to consider direction for this. So since the police car is heading south, we do have to consider that as a negative direction. Otherwise, our math isn't going to work out the way that it's supposed to. Because whenever you solve this equation that you have here, you would actually add the 36 to get 56. And then divide both sides by 0.8. So 56 divided by 0.8 is going to give you your 70 miles per hour. So here's my interpretation. At the moment, when, and actually rather than writing all of that out, at the moment in question, the car is moving at 70 miles per hour. So at the moment in question, the car that's speeding away from the scene is moving at 70 miles per hour. This one is extensive, and I know the derivative can be a little bit difficult. If you went back and found r, then you could have just taken the derivative of the r squared equation instead of the r equation. That might have made things a little bit easier. Okay, lastly, the last example we are going to do in the videos. Example 4, water runs into a conical tank at the rate of 9 feet cubed per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So I want to know, how fast is the water level rising? Well, water level, when you're talking about a cone, is going to be your h. It does say that this cone is point down. So it's point down, it's standing that way. I know that the overall radius is 5 and the overall height is 10. However, let's say, I have water level in here. When I look at the water level, that's going to be some other radius, and then I have some other height. So the thing to remember here is the 5 and 10, those are not fixed values. The 5 and 10 are going to be changing depending on what your water height is. So even though my overall radius is 5 and my overall height is 10, wherever the water level is, it's not going to be a radius of 5 and a height of 10 unless I have completely filled the container. One thing that this problem does not address is the rate of change of the radius. It says nothing about how the radius is changing. So radius is a variable I am going to have to eliminate or substitute for whenever I look at my equation. So we're trying to find dH dt when it says the water is 6 feet deep. So when h is equal to 6 feet. It says nothing about R. The normal equation for volume of a cone, which we already talked about in the previous video, is pi r cubed r squared h. I have to get rid of that r squared. I can't use the r squared in my problem because it's not appropriate. There's no radius other than the full radius. I don't actually know what the radius is going to be there, so I need to get rid of it. The bigger thing is I don't know what the rate of change in the radius is. But because the radius to the height has an overall ratio of 5 to 10, and the way that a cone is set up, it doesn't say that there's anything irregular about it. That means that any radius over any height at that given moment, whenever it has water in it, is always going to have a ratio of 5 to 10, which means 10R is always going to equal 5H, and R is always going to equal half of what the H is. You can use that and substitute in and replace the R in your problem with your H variable. And again, the reason we have to do this is because radius is not referenced anywhere as far as the rate and how it's changing. And the radius also isn't fixed. The radius is going to be changing as this cone gets fuller and fuller. So I'm going to replace the R with the 1/2 H. I am going to go through and simplify that. So I'm going to square it, and I'm going to pull that part out so that I have something more simple whenever I take my derivative. So 1/2 squared is 1/4 times pi over 3 is pi over 12. Then I have h squared times h, so that's h cubed. Now I can take my derivative. So dv dt is going to be pi over 4 h squared times dh dt. It doesn't quite look like an h there. I'm going to make that look a little bit nicer. Now I can go through and plug in. I am solving for dh dt. I know my dv dt is 9. That was given in the original problem. My h is 6. And I'm just going to write that over here. So 6 squared is 36. You're going to have that divided by 4 because you have the pi over 4. So I have 9 equals 9 pi dh dt, which means dh dt is equal to 1 over pi feet per minute, and that's approximately 0.32. feet per minute. So again, you can make the statement, at the moment in question, when the height is 6 feet, the rate of change of the height is 1/pi feet per minute, or 0.32 feet per minute. As I said, related rates can be difficult, especially when it comes to setting up the questions. So I do encourage you to seek out extra sources. If I get a moment, I'll try to add some Khan Academy videos that go over this type of thing. I know there's some good videos on YouTube as well that go over different types of related rates. So go back through, watch the videos, and as with everything else that we do, reach out to me if you have any questions.